Right. So directional derivatives and the gradient. So the directional derivative answers the question that is rather natural to come up with. So what you'll recall with partial derivatives is we talked about taking the derivative if we traveled in the x direction or if we traveled in the y direction. But when we have a function of two variables like this, or maybe three variables, maybe more, you can travel in a direction that combines these two directions, some direction that is a combination of both x and y, as in this picture. So the question would be, well, how would you define the derivative in that direction that isn't um, in one of these coordinate axes? And that's the directional derivative. So the definition of the directional derivative is this. So given some unit vector u that is going to be the direction that you're trying to travel in, and we use sine theta, cosine theta to kind of enforce the fact that this is a unit vector, then the directional derivative, which is denoted like this, it's d with a subscript u being the direction vector, of the function f, and then we can evaluate at a particular point AB. Well, I guess AB is down here, and then this would be if you graphed it, if you introduced the z coordinate, which is the evaluation of f at the point A, comma B. Right, so the derivative at this point is defined to be this difference quotient. So you can see that it looks quite like a difference quotient. You have f after you've traveled by a step h minus f of where you start at all over h. So maybe one thing we can do here is we can reason about why exactly why exactly it's like this. So notice that theta is defined here. Now if we what we're doing is we want the length of this vector to be h. Let me try to make that a bit, maybe I should zoom in. So we want that to be h. And let's make that into a right triangle. Then this side has length h cosine theta by trigonometry, I suppose. So the adjacent over hypotenuse is cosine of theta, so you can divide these two and you get that quantity. And then if you do similarly with the other side, well, to capture the amount of travel in the y direction, you would draw this right triangle. You basically you're projecting h onto the y vector, and then you end up getting let's see. So this is the length. This has length h, and then this angle ends up being the same as this angle. This is what is it called? Interior angles, parallel sides. That kind of that theorem from geometry says that this angle is congruent to that angle. And so this is the angle theta, and this is the side h. This is the side we're after, so that's the opposite side. That makes that this will have length h sine of theta, right? Because it's opposite over hypotenuse is equal to sine of the angle, and the angle here is theta. So this has length h times cosine theta. This has length h times sine theta, and so we've broken the vector h into its components in the x and y direction. And so that's why we end up having these steps of size h times cosine theta and b times h sine theta. I guess you could also have thought of it as taking it in this component form already and forcing it so that it has length h. Then it's just you multiply this by h since this has length 1. Okay, that's an easier way to think about it. Anyway, so yeah, this is a difference quotient, and so yes, this is the limit definition of derivative, but for higher dimensions. And well, just like with in Calc 1, the limit definition of derivative is rather bothersome to use, right? You only use it for like one or two problems, and then we give you a whole bunch of rules. Well, um, in this case, we actually have this other property. So it turns out that the directional derivative can be written as a linear combination in terms of the partial derivatives. So that's the partial derivatives are coming into play that we learned. So the x derivative multiplied by the um, um, amount of travel in the x direction times the y derivative, or plus the y derivative times amount of travel in the y direction. And then what you can do with this is notice that this can be written as a dot product, and this will be useful because this will relate to the gradient. So, and you can see that this is the direction vector that we started with, u. So this ends up being what we call the gradient of f. I mentioned something about the proof, so I didn't want to copy it down, but it basically it uses chain rule and kind of cleverly defining an auxiliary function g of t and setting up a chain rule from that, and then from that you can derive this property. So if you're curious about this at all, you can look at the proof that is provided by the book. You might need to clear up some things, and I think that there's a couple typos, but yeah. Okay, and here's a very important remark, right? So in this definition, right, we are, I guess I should color this. We're asserting, or we have this important assumption that the vector u is a unit vector, that it has length 1. So if in any problem statement you're being asked to calculate the derivative in some direction given by some vector, but that v, but that vector doesn't have unit length, the first thing that you need to do is to normalize that vector, make it a vector of unit length. Typically, what happens in the way that these problems are described, the non-unit length vector is denoted with some other letter than u. So like in my instance, I'm using v here. So, and then when you normalize it, you end up using the letter u to kind of emphasize the fact that you have a unit vector then. And then once you have the unit vector, you can then go through the process of computing it by using essentially this formula, but I'm going to write it in a slightly different way, and that is the formula that I would reach for. Okay, so let's see. The gradient, right? So this vector, which is this guy, this vector has a name called the gradient of the function f, and it's denoted with this triangle. This triangle is called nabla, and it's actually important that this triangle is facing this way. There's actually another mathematical operation that looks like this, and that's called the Laplacian. And we're not going to talk about that because that's, I guess, kind of deep in the weeds of vector analysis. But we have this guy. We have nabla, also sometimes pronounced as del. Okay, and well, this is the definition in if you have a function of 2 variables, if you have a function of 3 variables, you can see the pattern. And what will be useful for later on is actually if we can think of this symbol, this nabla, as being a vector of partial derivative operations. So this is why this is an abuse of notation, because this is not really a vector in any sense that we're familiar with, right? We're used to a vector populated with numbers. We're used to a vector populated with functions. That's called a vector valued function. But this thing, it's populated with what I guess would be called differential operators. Your entries are derivative operations. So it is a bizarre entity, but if we just kind of accept it symbolically, then one thing we get is that the gradient looks like this. It's as though we when we apply f on the right to it, we can pass the function through to each of the components, meaning that we end up taking the partials of the function f with respect to all of the variables that the function takes. So if f takes the values x, y, and z, then you have partials in terms of x, y, and z. I guess you could also imagine if, well, I get in a different coordinate system, I think the formulas actually differ. So I was gonna say something about, like, say spherical, but that might be a bit dangerous. Might be incorrect. But so, like, if you had 4-dimensional space, x, y, z, and maybe an additional w, say, then there'd be a df dx, df dy, df dz, df dw would be the gradient. Okay. And yeah, so we will later on see that this is also very nice in terms of having a way for us to remember these other two operations, divergence and curl, that will be covered quite a bit later. Okay, but so back to the gradient. So what's going on here? This is me rewriting the formula here. Okay, so this is actually the gradient, and I don't know if I want to actually just write that here. I guess I can. So yeah, this guy is gradient of f dot with u. Wait, is my cursor? Oh, that's why. Okay. I think they're messy today. Okay, yeah. And so yeah, that is what I just wrote right here. So the directional derivative in the direction u is f dot. These should be bold. Well, okay, I'll fix it. Just vector. Yeah. So yeah. So gradient of f dot product with the vector u. And this is to emphasize, well, here we didn't really specify a particular point. So technically, this would take x and y in if we're sticking to 2 dimensions, x, y, z if we're sticking to 3 dimensions. So that is technically something that we aren't going to talk about yet. It's I think, hold on, this is a vector field. This dot product is going to give you a scalar. I don't know. There's a slight difference between these things. Mainly, we'll be focusing on when we actually are plugging in at a point. In which case, this will grad f at a point is always going to be a specific vector, and then you're going to dot it with a unit vector. So this will always be a quantity, a number, which is what you expect out of a derivative operation, right? Derivative is supposed to be rate of change as you travel in some direction. So it should be a number. And this kind of checks out if you do the type checking, right? An actual vector dot an actual vector gives you a scalar. Okay. So okay, here's a concrete example. So we're asked to compute the gradient of the function f given here, evaluate at this point. So to start with, we compute the gradient. Okay, so that's just going to be a bunch of partial derivatives. So this is the partial derivative with respect to x. You can see that, well, because this is an exponential function, the exponential function sticks around. And then we have a 2x from chain rule that we take the derivative of, which introduces a 2 into the first factor. For this guy, we're taking the y derivative. That's going to pop a 3 out from chain rule. And then for the last guy, we're taking the z derivative, and in that case, this exponential is considered to be a constant with respect to differentiation by z. So then we just take the derivative of the function z with respect to z. That's just 1, and so we end up with this. Let's see. So this is a vector valued function, right? Then we take that and we evaluate it at the point that we're told to plug in at. And so that's, the values are chosen nicely so that the exponential is all to the power 0. And then, yeah, you got multiples of z, which is 4, so you can, yeah, it's a straightforward calculation at that point. Okay. Right, here's another example. So instead of gradient, this time we're talking about the directional derivative, right? So, which I mean relies on the gradient. So you're given a function f, x times e to the y. You're given a point p and a direction vector v, and you want to calculate the directional derivative in the direction of v. Okay, so in this situation, v is not a unit vector, so we need to start by normalizing it. All right, so divide by its magnitude. 2 squared plus 3 squared, 4 plus 9, 13, so square root of 13, and then you just push that scalar in. So this is the unit vector in the direction of v, and we'll use that in the computation. So the directional derivative, denoted like this, we use the formula for it in terms of the gradient. So gradient of f evaluate at the point. So the point, I'm just copying down the actual coordinates of the point, and then dot product with the direction vector. Computing the gradient. So let's see, the gradient here, I'm just sort of doing it mentally and then going to plug it in at the point. So yeah, the x derivative is just going to be the exponential e to the y. The y derivative will be x times e to the y. Yeah. And then we plug in at the point x comma y is equal to 2 comma minus 1. And that's going to give you this vector. And then u is that, so we just bring it down, and then we take the dot product. So the e goes downstairs, the root 13 sticks around, and you are left with 1 times 2 plus 2 times 3, so 6 plus 2 is 8. And so you get that quantity. Okay. Right. Now some properties of the gradient. So I try to explain how we know these properties, but you can kind of just remember these properties. So first, let's go through how we can derive them, how we can figure them out. So recall that way back in the beginning, we had this formula relating the dot product of two vectors to and the angle between them, cosine of the angle between them, right? So notice that we have a dot product here in the definition for the directional derivative. So if we use this dot product angle formula, we end up with this expression, right? Magnitude of these two vectors multiplied together, and then multiplied by cosine of the angle between them. And, well, u is supposed to be a unit vector, so it disappears. It's just the value 1. And so we end up with this quantity. So the directional derivative is the magnitude of the gradient times cosine of theta. And what's important about that is actually, what's important about that is, well, we can think of cosine as dampening this value. So, call that cosine is always between -1 and 1. So for some angles theta, on the unit circle, cosine will take the value 1 at this point, and it'll take the value minus 1. I guess I'll use a different color for that at this point. And then in between, it ranges through all the other values. And what that ends up doing to the magnitude is it dampens it, right? So at maximum, you get the entire value itself. You can get 0 if you're at these parts of the unit circle, where theta is equal to pi over 2 or minus pi over 2, otherwise called 3 pi over 2. And you could get negative of this value at theta equals pi, where they're separated by 180 degrees. So what does this mean? Well, so what we can do is we can then interpret what that angle represents. So the angle theta is the angle between the gradient of f and the direction that we're taking the derivative with respect to. So that means that the directional derivative is maximized when cosine of theta attains the value 1, which is what happens when theta is equal to 0, which is what happens when these two vectors are completely aligned with one another. How should I, maybe I can kind of diagram something about this as well. So, right. So you might have this kind of situation. And what happens is the value of the directional derivative is maximized when theta is equal to 0, when they are completely aligned with one another. And it is minimized when theta is 180 degrees, when they are actually opposed to one another, opposite directions to one another. And so that's what I say here. So, and then not only that, you can actually then determine the value, right? So when theta is equal to 0, the cosine of theta is equal to 1, so then the directional derivative is equal to the magnitude of the gradient evaluated at the point. So that's this statement here. The maximum value for the directional derivative is the magnitude of the gradient vector evaluated at the point. And this is kind of the way that I memorized the statement. The gradient vector points in the direction of steepest ascent, right? So if you want to maximize the directional derivative, then you want to be moving in the direction of the gradient, because the gradient is pointing at the direction where the function is increasing the fastest. If you deviate from that direction, you end up you'll be increasing at a lower amount, or maybe even decreasing if you kind of go the opposite direction around. There's actually there's a picture down here that kind of illustrates this. So if the gradient ends up, how should I say? So the input space is this xy plane, right? But the overall behavior of the function is this paraboloid-looking thing. So the gradient is this guy. It's pointing this way. You can see that the negative of the gradient is pointing the opposite way. And then if we kind of view what's happening on the function, well, the gradient is pointing in the direction of steepest ascent. If you deviate from that direction, you'll be increasing, but at a lesser degree. And then if you kind of pass through these places where you're perpendicular, you actually have no change. Your derivative is 0. If you pass through that, then you end up with derivative being negative. And so you're decreasing rather than increasing. I think there might be one more thing to say here. The maximum rate of ascent is the magnitude of the gradient vector. Yeah. So yeah, these are the properties. Well, this is one of the properties. One of the collection of properties. You can see that they're related, so it's easy to kind of package it all together as one thing. The gradient is the direction where the function is increasing fastest, or the gradient is the vector that is pointing in the direction of steepest ascent, and when you take the magnitude of the gradient, you get the actual rate of change. Right. Right. Okay, and here's an example that uses these properties about the gradient vector. So you're given a function f, written as such, and a point p. Find the unit vector that points in the direction of maximum rate of increase at the point p, and determine that maximum rate. Right. So the wording is maybe not optimal, but it's asking us to do exactly what I pointed out. So the direction of maximum rate of increase, right? That means you're making the derivative maximum. You're maximizing the derivative. So the direction that maximizes the derivative is going to be given by the gradient vector. These are not bold at all. So so what you do is you compute the gradient, and then you evaluate it at the point. So computing the gradient, derivative with respect to x is going to be 4x cubed y to the negative second. Derivative with respect to y is going to pull out a minus 2 y to the negative third, x to the fourth. Yeah. And then you plug in at the point, which is arithmetic, so I'm going to not bother with that. And then the problem asks us for the unit vector pointing in that direction. So this is the direction, but to capture the direction as a unit vector, we just normalize. So run through that process, we get this. And then the problem asks for the maximum rate. So what is the actual rate of change? Well, that's given by the magnitude of the gradient vector evaluated at the point. So we take the magnitude of this vector. So then that's this calculation, and that's simply 32 root 2. Yeah, these two double up, you have a 2, and then the 32 squared can get pulled out of the square root. So it's just this. Yeah. Okay, and this is the last property, which actually I already alluded to when we were looking at this picture here. So the property is that the gradient vector is normal to level curves. Now, we don't have an exercise that uses this, but I thought this was worth pointing out because this is actually the fact that allows us to create, or allows us to introduce this method, the Lagrange multiplier method, which it's a way of finding local extrema to the function. So we'll be seeing just like in Calc 1, you learned about absolute min, absolute max, local min, local max, how to like optimize a function, maximize or minimize a function, either on a closed domain or just entirely using like first order test and second order test. There are things analogous to that, which will be, I think, the next set of topics after the second exam. And Lagrange multiplier method is one of the ways to find these mins and maxes when you have a function and you have a constraint. So we'll get to that in a couple of days. Okay. And yeah, the formula has to do with this fact that the gradient is normal to the level curve. The level curve is actually the constraint. And then, I don't know, I'll try to explain it when we get there. Okay. I guess that's